All right, welcome back to the deli. Sorry, welcome back to the drive-thru. We had a little accidental button pushing there, so now this is part 2 of the video. Okay, example 2. Hungry? Stop by the deli. Get yourself a pastrami sandwich on rye with 2 pieces of Swiss. Stinky, delicious Swiss cheese. All right, so if you followed the last example, we did something that was unnecessary. Now we could only do this with a triple integral or a really, really funky double integral. So it's easier in triples. But first we got to figure out what the heck this thing looks like. So set up a triple integral to find the volume of the solid with the bottom. So does anyone remember what z equals x squared plus y squared is? It's one of our oids. It's a paraboloid. Okay? So like that. Okay? The top is what? A sphere with a radius radical 6. So I'm assuming it's going to intersect it somewhere. Okay? We've got to figure out where these things intersect to get a really good idea of what this thing will look like, but I'm thinking it's just going to be like that. Can you envision that? Okay? So, to find out where these things intersect, what do? Like any other 2 equations? We set them equal to each other. So where does x squared plus y squared equal square root of 6 minus x squared minus y squared. Okay. This is tough. Took me a little while to think about how I was going to do this. Obviously, one system, or one equation, 2 variables, so that's a bad start. But what we really want to know is we just got to get an idea of where they're going to meet. So what we really want to know is, where is that? So instead of setting it up like that, isn't that true? Isn't x squared plus y squared equal to z? So then we could write it like this. Right? Square both sides. No, shoot. That's a z. That's a z. That's a z. Right? Z equals x squared plus y squared. Not z squared. Z does. Right? So you got z squared plus z minus 6 equals 0. So z equals negative 3 or 2. And all we're worried about is where it hits in the positive. All right, Ratchet, I'll factor it for you. Since we have this on video, this is the one time all year that I'm right and you're not. Right? That Ratchet correction was sponsored by the deli. All right. All right, so.
Anytime that he is right and you're not, just remind him of this.
I won't. No, he's not. Okay, so. Now, what the heck is that telling us? This is where, like, I'm kind of proud of actually understanding this stuff now. So, at z equals 2, they intersect. Now we understand that. So then what I had to do was kind of go back to my understanding of level curves. If you slice this thing at z equals 2, then project that thing, that'll give you the level curve on the xy plane. That's what we're looking for, is our region. Okay? So, take z equals 2 and plug it in for this, and what do you get? Okay, now, plug it in for this one. You better get the same thing because we just set them equal to each other and solve for it. Okay? But do you? Yes, you do. You get a 4 here, and you get x squared plus y squared equals 2. So what that is when you slice this thing, I'll use pink, then the region, the level curve below it is the circle with radius what? Radical 2. So what that did was give us our aerial look. Does that make sense? That's where you kind of understand level curves. That hopefully makes sense. So now I think we've got enough information to set up our triple integral. Once again, I'm going to go dz, dy, dx. I think for this particular one, the x is easiest to figure out. So what's x going from to what to what to what? X goes from negative radical 2 to positive radical 2. Okay, what's this function right here? Y equals right? Radical 2 squared minus x squared, so 2 minus x squared. All right, so it's going to go from negative radical 2 minus x squared to positive radical 2 minus x squared. Now what's going to go here? 0. Not 0. The z values inside of this thing don't go from 0 to something. They go from one function to another function. So what goes on the bottom? Yep. Okay? And on the top? And that's an example of one that I don't think you could do with a double integral. You'd have to do all of this inside the double integral, which is kind of what we were doing at the end yesterday. And then, yes, excellent. That's a 1 in there, okay? You would not be expected to solve that, okay? Well, you know, that's something that you should probably play with. If you're good enough, if your calculator is good enough and you can figure out how to do that in your calculator, you're going to have a big advantage over, let's say, me, because I don't know how to do that or have that kind of calculator. Okay? But, okay, I'm going to pause this. So now let's see if we can get to center of mass. All right, so center of mass, remember, is equal to x bar, comma, y bar, comma, z bar. And now we're dealing with real-world shapes. The laminas were confusing. It was an area that we treated that had volume, and that's just counterintuitive. So now this should make more sense, okay? We're not going to go through each equation, but if you remember, we did our little teeter-totter thing. We started out, remember it was me, with a front butt for some reason, and then there was Mr. G, okay, and this ended up being mass times, this is x bar, this is x1, this is x2. Wasn't it my mass times my distance has to equal Mr. G's mass times his distance? Right? Isn't that right? And then to find x bar, we ended up doing, let's see. Well, it was already in the other video. It was basically the sum of the products over the mass. You remember that? All right, so that's what we're doing here. So, I am. It's rocking. You're fine. I guess that's the terminology. Like, it's still over a region. We take our distance from the YZ plane, which is our x-coordinate. We multiply by some density function. Now the density function is of 3 variables. And then now this thing is d what? dV for volume, okay? But we're not done yet, remember? Then you got to divide by the mass. So you divide by the triple integral of just rho. Remember, rho is a density function. So that's how you find x bar. Hopefully that kind of translates pretty easily. Okay? Y bar and Z bar are the same thing, but you multiply by a factor of Y and a factor of Z. Remember that X represents the distance from the from the YZ plane, and that's just like this. That's what this is. Okay? Are you laughing at the front butt? Is that what you're laughing at? Why do I have a butt in the front? Right there. Looks like a butt. Maybe I am standing behind. Okay. All right, so now let's talk about moments of inertia. All right, so I understand why the book used such confusing notation, but now I kind of understand it. Okay, my was, I think, this. Right? That was an object's moment of inertia about the y-axis. What are you learning about in physics? The moment of inertia, what's the equation? It's some constant times the mass times r squared. What does x represent? The distance from the y-axis. That's the radius from the y-axis. That's why they were that's why these things are switched. Okay? And then everything else is the mass. Right? It's the integral of density times volume. The reason this was confusing is it looks like it's times area. So now we're going to talk about mx because we just did x bar and we're just sticking with x today. Okay? Triple integral. I know there's a region there. Do you remember the Pythagorean Theorem in 3D? That was chapter 10. D equals square root of x squared plus y squared plus z squared. It's just a clean little... So what's the distance from the x-axis at any point? Exactly. Oh yeah, you're right. This should be an I sub x. I wrote this wrong in the first place. I sub y, moment of inertia. Okay? So now we're talking I sub x. I sub x is the moment of inertia around what? The x-axis. Okay, so inertia is your resistance to moving in a plane. So let me just tell you that another way to write x bar in our book is they write it as the moment in the YZ plane. That's the same thing. Okay? So your moment of inertia is your resistance to movement. It's pretty much directly dependent on your mass. because gravity's the same for both of us. My moment of inertia is bigger than yours, which means that if someone came and pushed you, you might move, and if someone used the same force on me, I might not. I have a bigger moment of inertia than you do because my mass is bigger. It's not a time. It's a bad word. It's a bad word. Okay? That's your planar inertia. Okay? Your moment of inertia is your resistance to movement in a rotational environment. Okay? So in this case, this would be your resistance to rotating around the x-axis. Okay? Does that make sense? And it's directly related to your mass and the distance that you are away from something. So the further away you are from something, the bigger your moment is, the less likely you are to want to rotate around that thing. Which is why when the figure skater pulls her hands in, she or he spins faster, right? Well, that's conservation of energy, but same concept. I think it is. Okay. Okay, so after this, we multiply by rho. So this is our density function. And then dV, and that's it. Okay? You understand that? And that's everything from today. Now, the word on the street is that these are really good problem selections. So number 3 is set it up. Number 3 is evaluate it by hand. It's pretty easy. 13 is just set it up. 15 is just set it up. And then if you keep working in order, they say 23 kind of ties together all the problems. And they say it's a good-looking problem. So that's what they are. I haven't done them yet. Can I get a Friday boom from my small class?